In this video, we'll introduce the neural network language model. In the previous video, we discussed n-gram models, and in particular, we talked about the fact that while in an application to get a good model, we want n to be large. If n is large, then we start suffering from the problem of data sparsity, which means that it's quite likely at test time that we'll be faced with a context corresponding to words that we've never observed at training time. And while there are some smoothing approaches for improving n-gram models, these can help the model perform much better, but data sparsity is still an issue. And so what we'll see in this video is a neural network language model approach to this problem, which is actually going to do perform better than a regular n-gram model. So the idea is actually exactly what I've explained before in the context of learn word representations. We're going to train a neural network that will take a representation of the context, and at its output is going to produce the conditional distribution of the next word, so the word appearing to the right of the context. And at the input of the neural net, we'll just put the concatenation of the vectorial word representation of each of the words in the context. So, in more detail, in the neural network, the first thing that we do is that we take the IDs of each word in the context, and then we look at our lookup table to extract the vectorial word representations of each of these word IDs. So in other words, we take the ID here and we look at the corresponding row in the matrix C, and we put that as the first vector in the context. And we do this for all words in the context, concatenating then each of the word representation to get our X vector, which is going to be the input of our neural network. And then the rest of the computations are the regular computations we do in a feed-forward neural network. So we take the vector X, consisting in all the concatenated word representations, multiply by the matrix, say W here, plus the bias, then some nonlinearity. So in this work, tanh was used. And then to get an output, we just multiply that hidden layer by the connections between the hidden layer and the output layer, and then apply a softmax nonlinearity to get at the output the distribution for the next word. So the if output, so the if element in that output layer here is going to be the probability that the next word WT is the word with ID I. So this model was proposed by Yashar Benjo and his colleagues in 2003. It's also in this work that the idea of learning word representations was first presented. And again, in this model, then when we train it, we'll actually train not just the parameters of the neural network, but also the parameters inside the matrix C, the word representation of the different words. Now, the reason why this model is better at fighting the data sparsity problem for large N, for large context sizes, is that the neural network is actually potentially able to generalize to contexts that have not been seen in the training set. So here's an example to illustrate why. So imagine that we wanted to evaluate the probability of seeing the word eating after seeing the words the cat is. Now imagine that the foregram the cat is eating, which we would need in a regular n-gram model in order to assign a positive non-zero probability for the probability of seeing eating after the cat is. So imagine that this foregram is actually not in the training corpus. But imagine that the dog is eating is actually in the corpus. Now, if the word representations cat and dog are similar, and if the neural network has learned to predict a good probability of seeing eating after the dog is, then if the word representation of cat and dog is similar, then it should also give a good probability, a similar probability in the context where instead of dog we have cat. And that's because since the part of the input that corresponds to cat is similar to the part of the input corresponds to dog, and since for the other words in the context the and is, they're exactly the same words, then the neural network should have a similar output and thus generalize well to that case. Now, then you might ask, well, if the neural network in its training data hasn't seen the cat is eating, but has seen the dog is eating, why should it actually learn that cat and dog should have similar representations? Well, maybe in the training corpus, while it hasn't seen the cat is eating, it actually has seen the cat was sleeping. And then maybe it also has seen the dog was sleeping. So from these two observations, and it has learned that for both the cat was sleeping and the dog was sleeping, it should have some meaningful probability of seeing sleeping after the cat was and after the dog was. So that's a signal that perhaps the representation of cat and dog should be similar. So because of this, because cat and dog maybe in the training set in other contexts, cat and dog would appear in similar contexts, then it should learn similar representations for cat and dog. And so for that reason, we can expect that it would be able to generalize well for this example, even if the specific context has not, this exact context has not been observed. So in that sense, it's not as much relying on explicitly seeing exactly the given context for which we have to evaluate the probability. For that reason, it should be able to generalize to these new contexts. Now, a few words about actually performing backpropagation in this model. Now, we already know how to compute the gradients of, in particular, the linear pre-activation of the hidden layer, which is just this. So L would be the loss we're optimizing. We're optimizing the negative log likelihood, so minus the log of the probability of the next word. And so with regular backpropagation, we're able to compute that gradient. Now what's next is that we have to take that gradient and backpropagate it to the word representations. Now in my notation, I'm going to note Wi, capital Wi, as the submatrix that connects the word with relative position I with respect to the word we're trying to predict, Wt. So capital Wi is the matrix connecting Wt minus I with the hidden layer. So we can show that the gradient of any word representation CW, so for any word W, is going to be, so this expression, where we sum over all relative positions in the context from the I equals 1, so that's this word here, to I equals n minus 1, so that's this word here. So we sum over all relative positions, and then if the word at that relative position is the word W, so this W here, then we add the gradient at the hidden layer multiplied by the transpose of the part of the matrix, the part of the connection matrix that connects this the representation of the word at relative position I with the hidden layer. So that's Wi. So that expression should not be so surprising. We know that if we've seen in a regular neural network that if we compute a matrix multiplication, so for instance, we take that hidden layer multiplied by a matrix, then the gradient with respect to the hidden layer is going to involve multiplying the gradient at the layer above by the transpose of the connection. So for the same reason, that's why we see these terms appearing. Now the reason why, and I'll remove some ink, the reason why we have a sum here and we have to sum over all position is that the word W might actually appear in more than one position in the context. And also it might actually not appear in some given context for some given training example corresponding to one context in the following word. So for each time it appears, we get this gradient contribution, and then we accumulate those to get the gradient of the word representation. So that's for computing the gradient of the word representations, and of course the gradient for all the other parameters in the neural network, so the matrix W here, the matrix here, and so on. All of these gradients that we need to compute, they're computed as usual in a neural network. And I'll just add some note. So these dotted lines here is just to note that, and that's something that they considered in that paper, we might have also direct or direct connections between the input layer and the output layer. That's a potential modification to the neural network that one might consider. And if you want more details about that, I suggest you go look at the corresponding paper. So let's do an example of the gradients, computing the gradients for a given context and its next word. So imagine we're training the neural network, and now we're trying to infer the probability of observing cat after seeing the context the, dog, and the. So for this training example, so this whole sequence of text corresponds to one training example for our neural network. We are trying to optimize the loss of minus the log of the probability of seeing cat given all the previous words. And so this is, we see here that this is a 5-gram model because we're considering the 4 previous words. Now imagine that the, which is W3 here, has an ID of 21, dog, which is W4, ID of 3, and W5, ID of 14, and the, which is also present at the absolute position 6, so that's W6, also again has the ID 21. Now, if we're interested in what is the gradient for the word with ID 3, so that's dog, then it's going to be the gradient with respect to the pre-activation of the neural network multiplied by the transpose of part of the input connections that connects the word at relative position 3. We take the transpose of that, and that's what we multiply with the gradient of the pre-activation. So indeed, dog is at relative position 3, so that's 3, 2, 1, that would be 4. So that's why we're taking that gradient of the pre-activation at the hidden layer, multiplying by W3 transpose. For 14, which is end, it's at relative position 2, so we take the same pre-activation gradient and multiply by the transpose of W2. And now for 21, it actually appears at 2 positions, that is at relative position 1, so right here, and 4, right here. So we have to add these two backpropagated gradients, the pre-activation gradient multiplied by W1 transpose, and then pre-activation gradient, again multiplied by W4 transpose. And then for all the other words W in our vocabulary, then their gradient for this particular training example would be 0. And so it means that for the vast majority of word representations, their gradient for that training example is going to be 0. So we won't actually have to update them. So in our implementation, we should only update the representations C3, C14, and C21. So instead of updating the whole matrix C, we should just update these rows in the matrix C. So the 3rd row, 14th row, and 21st row based on these gradients that we have here. So that's important to do this to get an efficient implementation. So when we're evaluating language models, a common evaluation metric that's used is the perplexity. So it's an information theoretic measure. I won't describe it. I'll just say that it's essentially the exponential of the average negative log likelihood of some given data set. So you know what's the average negative log likelihood. So you just take the exponential. Turns out it's the perplexity. And so again, the lower the number, the better, much like the average negative log likelihood. And so in these experiments reported in that paper on the Brown corpus, which is a well-known data set for language modeling, if we take an n-gram model, which is smoothed using a state-of-the-art smoothing method known as Nisser-Ne, we get a perplexity of 321. And with the neural network language model, we get a much lower perplexity of 276. So a gap of 50 like this, almost 50, is actually quite big in the realm of language modeling performances. And then in language modeling, also usually combining models, for instance, creating an ensemble of the neural network and the n-gram model by just taking the average of the probability of each model, also gives an even better performance. So we see that by just with the neural network, we already do much better. And then if we already had an n-gram model, combining it with the neural network actually adds even more. Now, a more interesting but a bit more difficult to do in practice and less straightforward way of evaluating a language model is really to evaluate it in a particular application that uses a language model, such as a machine translation system or a speech recognition system. And later work, so the initial work on neural network language modeling was in 2003, but actually much later, it's been shown that you can get really good performance of with a neural network language model that you incorporate into some standard model that does either speech recognition, as in this paper, or statistical machine translation, as in this paper. So I encourage you to look at these references if you want to see examples of the gains you can get from using a neural network language model in some given NLP system.